Welcome back everyone to part 2 of this video. In part 1 we talked about the basic introduction to Carey-Foster bridge. We have not talked about Carey-Foster bridge yet. I introduced you to the concept of Wheatstone bridge, which you already know, and then I talked about the balance condition of the Wheatstone bridge as P by Q equal to R by S, and then I talked about meter bridge and how that meter bridge gives us unknown resistance by finding null point of a meter wire, and you already know the formula. It's P by Q equal to L1 by 100 minus L1, and I have asked you to remember this formula. I'll be needing this today. And then I talked about the problems with this method. To be very brief about the problem is that the meter scale does not have greater precision than 0.1 millimeter, and so if the null point falls between say 50.7 and 50.8, it will not be able to measure that. We will not be able to measure that, right? And so the resistance will not be very accurate, and so this method lacks accuracy. And then I said that we can increase the accuracy by, of course, increasing the length of the wire. If the wire was 100, instead of 100 it was 1000, then of course the null point would have been obtained at 507.4, and that could be measured by us, right? But again, if it was 507.44, then I had to increase the wire to 10 times more again, right? And we cannot increase it because of such problems as you can see on the screen, and so it was not a great solution either. So we are looking for a solution here by which we can measure the resistance more accurately. And this is very important because, as I discussed in the last video, that if we cannot make a method where an unknown resistance can be very accurately measured, then we will not be able to use that method to calibrate new resistances, right? So we really need that method. And let's think in this way, that increasing the length was a very good way of doing it, but well, we cannot because of several problems that I already talked. Anyway, but we can think in that line, right? So let's see what's the big idea. Well, hold on, it says length of wire equal to resistance. Well, I already know that. How is that going to solve my problem? Okay, let me think. Is it saying that if I, instead of increasing length, I add resistance, it's going to help me? Well, just a sec. Where will I add the resistance? Oh, hold on, there are two gaps in the left side, in the extreme left and in the extreme right, so I can add two resistances there. But how is that going to help me? Okay, I'm getting it. Perhaps you are getting it too. The point is, think of that old example that I gave in the last video. Null point was obtained at 507.4. There were 10 wires, and the null point was obtained in the fifth wire at 7.4 centimeter. Do you get it? The point is, before that fifth wire there were 4 more wires, and after that fifth wire there were 5 more wires, and all those wires was equivalent to a resistance. So instead of using all that length, if I just put an equivalent resistance to the right side and to the left side and put a 1 meter wire in the middle, isn't that really equivalent to the 10 meter wire? Okay, you got my point, but it's not really convincing. Let me put my point again. The point is, so instead of increasing length of wire, let us add equivalent resistances on both sides. But you are not really convinced that this will help, right? I can sense it. But you have understood the point, that the case is equivalent. Okay, let's see an example, and let me just convince you completely that this really works. Let's take, for example, P in the top left as 1 ohm and Q is an unknown, but again, say you cheated and you know it's 500 milliohm, 0.5 ohm to be precise, and then you know the old formula. You can theoretically calculate the null point to be 66.667, which is quite obvious because think of it, if there is a 1 ohm on the left and a 0.5 ohm on the right, then the null point will also have to be 1 and 0.5, so it's like 2 times on this side, 1 times, it's a 2:1 ratio, so it's like 1/3 and 2/3 type of ratio, right? So it's obvious that the null point will be obtained at 66.667, right? From the left, measured from the left. I already talked in the last video that I'll always be saying about measuring from the left side. Well, the problem again is that practically we will never be able to get the null point on 66.667. I mean, the null point will be obtained at 66.667, but our scale will not be able to measure that value, and we will just be satisfied with 66.6, say. Somebody would have been satisfied with 66.7. Anyway, suppose he noted 66.6, and practically getting this L1, he calculated Q, and his Q came out to be 501.5 milliohm. You can check this, which is not quite same as 500 milliohm. And I'm not really going to repeat that how important is it to be as accurate as possible, because you can argue with me that this is just 1 milliohm, but the point is, again, calibration is really impossible if the instrument is even doing error of 1 milliohm. I hope you understand it right now. Anyway, but how does this in adding equivalent resistances on both sides help? Say I look at that picture on the top left. Say I open the gaps on the extreme left and extreme right, and I put 2 resistances there. I'll call them X and Y. What happens now is that P and Q, that P by Q ratio, will need to be balanced by the X resistance plus some wire on the left side, and by some Y resistance plus some wire on the right side. Do you get my point? So the condition for balance will be something like this. Well, lambda, I already talked about, is the resistance per unit length. So P by Q will be balanced when X on the left hand side plus lambda times L1, where L1 is the length measured from left hand side, divided by Y plus lambda times 100 minus L1. I hope you understand this. It's very simple actually. Now just put in 2 values for X and Y. For X, suppose you put in 1 ohm, and for Y, suppose you put in 300 milliohm. It's really a matter of convention. You could have put in any value. I'm just wanting to show you how this helps. Putting this, you can just simply calculate theoretically. You will see that the null point is 60 centimeter exactly. So forget theory. When you're going to do this practical, you're putting 1 ohm on the left side, you're putting 500 milliohm, which is Q, which is unknown, on the right side, and then you're putting an X and an Y. Instead of the last practical where you did not put XY, in that practical you obtained 501.5 milliohm, as you can see in the left. In this practical you're putting an X 1 ohm and an Y 300 milliohm, and now you're measuring the null point, and you will be theoretically getting the null point at 60 centimeter, and practically that is also available. So you will be exactly measuring at 60 centimeter a null point, and that will give you an exact value of 500 milliohm. You can calculate, and voila, I've got a great method. Do you understand how important it was to equivalently thinking of length as resistances? We will say that these resistances effectively increase the length of the meter bridge. So this is the novel idea behind Carey-Foster bridge. So let's get into Carey-Foster bridge. Well, you have seen this picture. If you haven't, well, it is in front of you right now. You can see that it contains a simple meter bridge. It's not really too tough to understand. The left hand side gap has been replaced with a X, the right gap has been replaced with a Y, where X and Y are variable resistances. P and Q are known fixed resistances. There is a commutator C, which actually helps in reversing the direction of the battery, and there is a galvanometer G, which touches the wire EF at the point D. The distance of D from the left hand side is measured to be some length. For a null point, say it is L1. For some other null point, say it is L2. We'll talk about this L1, L2 later on. So what are the points to note here? Number 1, the commutator C will be reversing the current whenever we need it. Well, will the reversal of current cause any change in null point? Well, theoretically no, because no matter which direction the current is flowing, the KVL remains the same. So the null point will still be P by Q equal to R by S, or as in this case, P by Q equal to X plus lambda L1 divided by Y plus 100 minus L1 into lambda. Then why are we doing this in the practical? Well, it's to nullify the thermoelectric effects. I'll really not be talking about them right now. You can think about it. We will definitely discuss that in class. What else to note here? Okay, as I already said, this point, lambda is the resistance per unit length, and let P be equal to Q. And say P and Q are measured beforehand. They are known standard resistances, say 1 ohm or anything. But say that they are fixed and they are known and they are same. And lastly, let the end corrections be alpha and beta for the left and the right side respectively. Well, what are these end corrections? They can be several things. For example, you can see in this picture that the wire does not exactly end where the 0 centimeter is marked or the 100 centimeter is marked. It goes beyond and it is connected below that copper strip. So this extra length also adds to some extra resistance. This is a reason we need to add some unknown alpha and beta, right? Apart from this, there are several other reasons. These copper connections may themselves provide some resistance. And again, there are something called contact resistances. And there are several such things which may add to this resistance, and so we don't know the value, and so we'll call them alpha and beta. Note that even in meter bridge case, it was there, and we could have again tackled it there, right? So I really did not go into much details about that because our practical at hand is Carey-Foster bridge. But the point is that alpha beta was present even in that meter bridge. Okay. Anyway, so let's really get into the practical. Carey-Foster bridge is started by putting a resistance X on the left hand side and resistance Y on the right side. It's a matter of convention what values you put, but there are some limitations to that values, and I'm not going to details of those practical limitations. We'll be talking about those practical limitations when we will do the practical class. This is more of a theory class. So let me just get into the balance condition. But it's obvious the balance condition will be P by Q equal to X plus alpha plus L1 lambda divided by Y plus beta plus lambda times 100 minus L1. Now the point is, how do I get rid of alpha and beta? I don't know them. Suppose alpha beta weren't there, and suppose I know P and Q, which is obvious, I know P and Q, and X and Y are variables which are put by me, so I know their value also. Then you can see that if I get L1 practically, it's just one step to determine lambda, and so definitely it's obvious that the practical wouldn't have been so big. The problem is I don't know alpha and beta, so I need to somehow eliminate them, and this is what we do to eliminate them. We interchange X and Y. On interchanging X and Y, the null point will definitely shift towards the other end. It's just like beam balance. If the weight is interchanged, the beam will be deflected to the other side, right? So the null point now shifts to some value called L2. You might think that this L2 is exactly 100 minus L1 because it's just a mirror reflection type of thing, but the point to note here is no, it is not. It is not, because alpha and beta are unknown and they are not really same, right? So L2 will not exactly be 100 minus L1. Otherwise the practical wouldn't have any meaning. Then alpha beta would be same and they would cancel and all that. Anyway, so now you note L2 again measured from the left hand side, and so the null point now is P by Q equal to Y on the left hand side plus alpha plus L2 lambda divided by X on the right hand side, so plus beta, which is the end correction of the right hand side, plus alpha plus 100 minus L2 into lambda. You can see that P by Q is present on the LHS of both the equations, so we can equate the equations. Now the rest is mathematics. This is what happens when you equate them. It's really not good looking because I'm afraid if I cross multiply there will be 12 terms on each side, right? And I don't want that. What I can do is a very simple trick. I'm just adding 1 on both sides so that the denominator goes on the top, and you can see that the numerators become equal on both sides. I can cancel them, and then I can cancel beta as they go on top, and then I can cancel 100 lambda. What I will be left with, you can just do it in a copy. I'll be left with this, and this is the formula for finding lambda. So using Carey-Forster bridge, you can put x on the left hand side and y on the right hand side and find out L1, the null point, right? And then you can interchange x and y, and you can again find out the null point. We will call that L2, and then simply calculate lambda equal to x minus y by L2 minus L1, and then repeat this experiment for another value of x, right? So this is the Carey-Forster's practical. As simple as that. We can make it more simple by making y equal to 0. That is, just shorting that path, just like it was connected during the meter bridge time. So the formula will simply reduce to lambda equal to x by L2 minus L1. And so we'll just have to change x every time. So suppose we take 5 values of x, which again I'm saying has some practical limitations, and I'll not talk about it right here. Theoretically, we take 5 values of x. For that we put x on the left hand side and y equal to 0 on right hand side and find L1. And then we interchange, that is, we now put 0 on left hand side and x on right hand side and find L2. And then we calculate lambda. And then again we take another x. For that x, we again put y equal to 0. We find L1. We again interchange. We find L2. And then we find another lambda, and these all lambdas will essentially be same, right? So we can find the mean. So that's what Carey-Forster bridge does. Well, now you'll ask, what is that commutator for? That commutator is for directing and reversing the current each time. Whatever I said right now, that is interchanging x and y and all, each time you'll have to change the direction of current as well. That is, when x is on the left hand side and y on the right hand side, we'll have to pass the direct current and see L1. And then when x is on the right hand side and y is on the left hand side, we'll have to pass the direct current and find L2. Again, we'll have to find out L1 by putting x on the left and y on the right, but this time by using reverse current. Well, theoretically it will be L1 again, but practically it might differ, and that is due to thermoelectric effects. But usually this comes the same. I'll talk about those practical troubleshootings later. So that's the practical, folks, but this is just half part. But honestly speaking, you have done almost 80% of the practical, because the rest is very elementary. What is left is that, knowing lambda, now you can simply calculate some unknown resistance. Let us call that unknown resistance as y. So since we know lambda, just rearranging this formula gives us y equal to x minus lambda times L2 minus L1. So this time we can just put an unknown resistance at y, and since we know lambda, by doing the same practical, we can put different values of x. We can find out L1, we can find out L2, and putting in this formula, we can find out y. So it's doing the same practical again, but this time instead of finding out lambda, we are finding out y. So that's all, folks. With this method, you can see that we can have extremely high accuracy and precision, because I already showed you that in the example, that if you take some proper values of x and y, you can get some exact readings in the meter scale. So it's really a lot of help for us. Thank you, George Carey-Forster. With that, I'll end my video. So thank you for waiting for so long. But there's a catch here. Well, you really waited for a long time, and you really listened to a much long video. So there is some surprise for you guys. there is something that I want to show you. It's really a big surprise for you, so prepare for it. The point is, this entire video was based upon something called the Wheatstone Bridge. It was discovered by Charles Wheatstone, as you all know. Well, but was it? I was looking through the papers of George Carey Foster, and in the original paper where he discussed his Carey Foster Bridge, which was released in 1872, actually in those days, sometimes papers weren't released. There were just proceedings on some royal meetings, and those proceedings used to be written down by somebody. And in 1872, Carey Foster actually presented his paper in a proceeding, and in that paper, after the paper reading was done, somebody stood up and noted, somebody called Mr. Latimer Clark stood up and noted that Carey Foster developed upon something which he called as Wheatstone Bridge, which he named to be Wheatstone's discovery. But you can see in the paper, which I will now display, I have cut a part of it, that Mr. Latimer Clark said he was sure they had all listened with pleasure and advantage to the paper just read. To his own mind, here his is Foster. To his own mind, it seemed to add one more proof of the great value of the system of measuring by Wheatstone Bridge, which was so indispensable to electricians. Then he goes on to say, it might surprise some to hear that the instrument Professor Foster had spoken was not the invention of Wheatstone. Yet it was proposed by someone called Christie, who proposed it 10 years before Wheatstone brought it second time before the notice of the public. Well, this is a big news, right? And a lot is written about Christie. He was attached to the Royal Military Academy, and he had many papers on electricity, and you can really find out about Christie. He did a lot of things, but as you see, history usually remembers a person who is more important and attaches his name to something. So we all know Wheatstone Bridge is discovered by Wheatstone. It's not really true, so it's a big surprise, right? So I think you like the surprise. You see, history doesn't really forget anything. If somebody somewhere is finding it up, you can always have everything back again. And right now, we all are a part of history. We are going through this quarantine period, and somebody someday in future will really find out what we were doing right now. What steps did you take right now? So really, I'm asking you to be very safe and act very responsibly. We all are part of our history right now. Who knows, someday you might really have done something right now which will really inspire you to do something better someday. Anyway, let's just sign off here. Please subscribe to our YouTube channel for such videos in future, and you can join us at Facebook at Delight Physics Lab, and in Facebook you can contact with each faculty. Let me just sign off.